During our last period of instruction, we discussed, among other things, voltage, current, and resistance, and we pick it up now with a discussion about Ohm's law. And Ohm's law is a very important electronic principle that ties together these three items of voltage, current, and resistance. George Simon Ohm expressed the relationship between current, voltage, and resistance in a long time ago, 1927. And this principle bears his name. Okay, what does Ohm's law say? Well, it states this, that the current that flows in a circuit is directly proportional to the voltage across the circuit and is inversely proportional to the resistance in the circuit. It is expressed mathematically like this. It says current equals voltage divided by resistance, and it's actually a little more common to see it written like this, that the V is expressed as E. So as we go through this course, if I write it as the E, which is my more common way of doing it, it means the same thing as V. But current equals voltage divided by resistance. So what's this say? The current that flows in a circuit is directly proportional to the voltage. So if R were to stay the same and I were to increase, then E would increase as well. Likewise, and we're going to forget about this for a moment, if voltage remained the same and resistance were to increase, then I would decrease. And likewise, if resistance went down, current would go up. And we're going to look at a few examples to make this a little bit more clear. The first one we're going to look at is that current is proportional to voltage. And what we have here is 3 meters that are set up, and we have a battery here. This is a voltage and this is a resistor, and we have the same scenario set up in all three. And what we're saying here is that the higher the applied voltage to a circuit, the greater the current will be. And so in this scenario, we're looking at this particular formula, I equals E over R. That is, current equals voltage divided by resistance. And in this case, we have a 10-volt battery, a 20-volt battery, and a 5-volt battery. And we're going to say that this resistance is going to stay the same. We'll say that this is going to be a 10-ohm resistor all the way across. So using Ohm's law, we would come in here and we'd say, well, the voltage is 10 and the resistance is 10. So given that, the current equals 1. And so here we have our meter, and our meter, for our purposes, we're going to say it is indicating 1 amp of current. Then we come to our next one here, and here we have 20 volts and resistance is 10, and now the current has gone up to 2 amps. Now remember, the part of Ohm's law that we're looking at is this part that says that voltage is directly proportional to current, and so you'll see a direct proportion here. We have 10 with 1 amp of current. When we double the voltage, the current also doubles. And in this case here, with the same voltage applied, and in this case the resistance drops to, the voltage drops to 5 volts, and the resistance is 10, so now the current drops in half, and you notice the meter here is going down. So in all cases, voltage is directly proportional to current. And if we were to graph this, let's see, if we had our voltages were what, 5, 10, 15, and 20, and our currents were what, 0.5, and let's see, we had 1, and 1.5 and 2, something like that. And in our first scenario, we had applied 10 volts across 10 ohms, and we had 1 amp of current, about right there. The next one we applied 20 volts and we had 2 amps of current about there. And then we reduced the voltage on the last one, and we had 5 volts and about a half an amp of current right there. And if we were to graph this, we would see that it is linear. As voltage increases, current increases, and vice versa. Now, the second part of Ohm's law said that current is inversely proportional to resistance. And so the rule here is that as current goes up, resistance goes down, and as current goes down, resistance goes up. And so let's take a look at this one. In this case, we're going to be looking at a stable voltage. The voltage is going to remain 100, and we'll say 100 here and 100 here. And we're going to vary we'll start out with 20 ohms, and then we will increase the resistance to 40 ohms, and then we're going to decrease it down to 10, and we're going to look at what happens in this particular circuit. So here we start out with 100 with 20 ohms, and that will give us, what, 5 amps of current. And then we're going to leave the voltage the same, and we are going to increase the current. Now, according to Ohm's law, they're inversely proportional, so the resistance was 20, it goes up to 40, so now there should be a decrease in current. And if we do the math here, we get about 2.5. So resistance went up, current went down, and here we're going to drop the resistance dramatically. It was at 100. We're going to drop the resistance down to 10 ohms, and now the current jumps quite a bit. Okay, so again, in this relationship, and remember these are the meters indicating the values. This was our starting point. We're showing mid-scale. We increased the resistance, current went down. Here we decreased the resistance and the current went up. If we were going to look at this on a graph, let's see, we started out with, what was our initial voltage? We started out with 100 volts and 20 ohms of resistance. Okay, so in this particular case, we started out with 20 ohms of resistance, and remember our current was 5 amps. And then we increased our current or our resistance to 40 ohms, and that decreased our resistance to about 2.5. And then we decreased our resistance to 10 ohms. Let's see, on our scale that would be about right here, and our current was at 10 amps. So you see, here we have an inversely proportional relationship between current and resistance. You see, we no longer have a linear curve as we did with voltage and current. Another important thing that we might note from this is that part of Ohm's law was this formula right here, that voltage equals current times resistance. And so in this particular scenario, we had 100 volts as the applied voltage throughout. We just changed the resistance, and if you'll note here, current times resistance here, 10 times 10 is 100, and 20 times 5 is 100, and 40 times 2.5 is 100. So this relationship of current times resistance is also a part of Ohm's law. And these are the three formulas we just talked about. It is imperative that you commit these three formulas to memory, and that when you look at circuits, you're able to kind of visually in your head just apply these formulas and get rough ideas of what voltages and current should be. So these are not optional formulas in the field of electronics. These are must-know, and they're really the foundation of calculations for electronic circuitry. Okay, the next one is electrical power, and we are going to, electrical power is a measure of the rate at which energy is used, and it's measured in watts. Electrical power is dissipated as heat. Based on Ohm's law, power calculations are determined with this formula right here. Power equals I times V, or you could say also I times E, either way. At any rate, current times voltage gives us the power in what we call watts. And when you get an electric bill, ultimately what you're paying for is the power that you have consumed, and it is measured in watts. Now, other variations of this formula look like this: I squared R. And if we were to, let's see, if we could derive this from this particular formula, if we say I times V, which is this formula right here, something that we'll notice is, remember from Ohm's law, voltage is equivalent to what? Remember, voltage is the same thing as I times R, isn't it? So if we replace I times R with V, and then we have our I over here, we can simplify this equation to say I squared times R. And so that is the same thing as this. And vice versa, we can go over here, and again, if we have I times V, and this formula right here, we can derive this formula. Now, what you might recall is current. Current is a function of, in Ohm's law, it is the same thing as voltage divided by resistance. And so if we replace I with V times R times V, we can derive the equation V squared divided by R. And so again, this is an equivalent way of calculating power. So you could use this formula, or this, and these three are stated right here. And here we have a simple circuit. What is the power dissipated by the resistor in the circuit below? And so let's see if I can bring up my handy dandy little formula, and let's see. So here we have, remember, to calculate current, remember we divided voltage by resistance. So if we said 100 divided by, and this is a 10 k ohm resistor, so if we said 10 0 exponent 3 and equals, we would have a current of 10 milliamps. And so according to our formula, power is voltage times current. So we have 10 milliamps. If we take that current times the applied voltage times 100, we will get 1 watt. Okay? And likewise, we had our other two formulas. Let's see, we said I squared R. We said I squared times R, or voltage squared divided by R. And if we brought it back our little formula, or our little calculator here, let's see. If we said we had a current of 10 exponent minus 3, that was 10 milliamps. So we said I squared times R. So if we square this times our resistance, which is 10 exponent 3, it should equal 1 again. And then we could do the other formula here. Let's clear our calculator. And if we said 100 squared, and we will divide that by the resistance, which is 10 exponent 3, we should again get 1. So we have 1 watt power dissipated by this, and we've looked at 3 different ways of calculating power for this particular circuit. Okay, next item we're going to look at is a subject called conductance. Conductance is the inverse of resistance. It expresses how readily current can flow through a material. The unit of measure for conductance is G. It's referred to as Siemens. At one time the unit of measure was called mhos, M-H-O-S, and that is ohms spelled backwards because it's the inverse of ohms. The relationship between resistance and conductance is expressed by, and you'll note here, G equals 1 over R. So whatever resistance is, 1 over resistance will be the conductance, and it's measured in Siemens. The pictured resistor has a resistance of 10,000 ohms. Its conductance would be 1 over 10,000 or 0.001 Siemens. Here we have some electrical quantities and abbreviations, and we've got 2 pages of these, and we haven't covered all of these subjects yet. In fact, I'll just briefly jump to the other one here. I do want to mention them here. I'm not going to go into all of them at this time. I want to give you a sense of what we're looking at, though, because throughout the course of this book we will be looking at all of these items. But for example, capacitance. The symbol for capacitance is C. The unit of measure for capacitance is the farad, and the abbreviation for farad is F. So if you're looking at electrical schematics, you might see C3. This would be indicating probably a specific capacitor, and the value of that capacitor would be 0.002 farads. Likewise, conductance, the symbol is G. Siemens, the abbreviation for Siemens is S, and G5 would indicate a device that has the 0.01 Siemens would be the value of conductance for that component. Here we have frequency, which is measured in hertz, and like I say, I'm not going to go over all these at this point. The F here means frequency, and the 60 hertz is the actual value of frequency in hertz. Let's see, let's jump over to the next page. Power, we've talked about power. Watts. Power here would be referring to a specific component probably, and the power is 150 watts. Resistance, the value of resistance R, 140 ohms. Voltage, V, form, this might be referring to a test point, equals 12 volts. Okay, in this lesson we have looked here at the electrical quantities, abbreviations, units, and symbols. We took a look at the value of conductance, and we found that conductance was whatever the value of resistance is, the conductance was effectively the reciprocal. We also looked at electrical power, and we tried 3 different ways of calculating the power for this specific circuit. We got the same results with all 3 formulas, and these were the 3 formulas we used. Power equals current times voltage, power equals current squared times resistance, and power equals voltage squared divided by resistance. We also looked at the forms of Ohm's law, and you will need to commit these to memory. We looked at the part of Ohm's law that says that current is inversely proportional to resistance, and we graphed that, and we measured it on a situation where we had a voltage that remained the same with a changing resistance, and we saw as the resistance went down, current responded in an inverse manner. Then we looked at the first part of Ohm's law that says the current is proportional to voltage, and we hooked up a current meter to a battery and a resistor. We left the resistor at one value, we changed the voltage, and we saw that the current changed in a proportional manner. And then we looked at what is Ohm's law. We discussed I equals V over R, or I equals E over R.